This fourth A group is also called as carbon family. Elements present in this group are carbon, silicon, germanium and lead. Tin and lead have got their symbols from corresponding Latin names stannum and plumb. In this topic we have to see the general physical properties, followed by general chemical properties, and then preparation properties and uses of individual elements. In the general physical properties, the first physical property is electronic configuration. The general electronic configuration of fourth A group elements is NS2, NP2. Coming to individual elements, carbon atomic number is 6, configuration is represented as helium followed by 2s2, 2p2. Silicon is 14 atomic number, electronic configuration is neon followed by 3s2, 3p2. Germanium is argon followed by 3d10, 4s2, 4p2. Tin atomic number is 50, krypton followed by 4d10, 5s2, 5p2. Lead atomic number is 82, electronic configuration is xenon followed by 4f14, 5d10, 6s2, 6p2. So, as you can observe from these electronic configurations, even though outermost electronic configuration is similar for the elements, number of electrons present in the inner shells, that is penultimate and anti-penultimate shells, differs from element to element. In properties, carbon and silicon are more similar, germanium and tin behave in a similar manner, while the properties of lead will be different from rest of the elements. Now, let us see the general analysis of variation of physical properties among fourth A group elements. Variation of general physical properties among the elements of fourth A group. The physical properties taken for the comparison purpose are atomic weight, density, melting point, boiling point, atomic radius, ionic radius, ionization energy and electronegativity values. Atomic weights, as far as concerned, they are continuously increasing from carbon to lead. So, the gradation or a change is a continuous increase in the value. The density, it depends on the allotropic form also. In form of a diamond, carbon has a density of 3.51, whereas in the form of graphite the density is 2. For silicon it is 2.33, germanium 5.32, tin 7.28, lead 11.34. So, overall density values are continuously increasing down the group if we consider graphite as the allotropic form of carbon. Then coming to melting point, the highest melting point is observed for carbon, then for carbon to germanium there is a decrease in the value. In case of tin there is abnormally lower value, and in case of lead it slightly increases. But overall variation of melting point among the fourth A group elements can be taken as a decreasing order. Boiling point, it is also continuously decreasing from carbon to lead. Atomic radius, it is lower for carbon, slightly increases and continuously increases up to lead. Therefore, variation of atomic radius is continuously increasing down the group. Ionic radius also follows the same trend. Here, the ionic radii of dye-positive ions are taken for comparison purpose. Coming to ionization potential values, carbon has highest first as well as second IP values. the IP values decrease from carbon to tin, and in case of lead there is a slight increase in the value. Electronegativity values, carbon has an electronegativity of 2.5 and the rest of the elements have got a constant value of 1.8. Therefore, here not much variation is there. From carbon to other elements there is a decrease in the value but in case of silicon, germanium, tin and lead it is a constant value of 1.8. Oxidation state values. Carbon and silicon, they exhibit a common oxidation state of +4, while germanium and tin exhibit both +4 as well as +2 oxidation state values. Lead shows only +2 oxidation state. That means oxidation state values are decreasing from +4 to +2 down the group. The reason is inert pair effect. Allotropy is also one of the general physical property. Existence of an element in different physical forms is called as allotropy, and the various different physical forms are known as allotropes. The property of allotropy begins in 4th A group, continues up to 6th A group. It is a common property of non-metals and is observed to some extent in case of semi-metals. In case of 4th A group elements, carbon allotropic forms we will study in detail. In nature, carbon is available in two distinct allotropic forms. One is called crystalline form and another one is called amorphous form. Crystalline forms are further three types: diamond, graphite and fullerenes. There are many amorphous forms of carbon like coal, coke, charcoal, gas carbon, lamp black, etc. Coal is formed in nature by the decomposition of vegetable matter under the layers of earth at high pressure and temperature. When coal is subjected to destructive distillation, coke is obtained. This charcoal, depending on the source, is given different names like animal charcoal, sugar charcoal, coconut charcoal and wooden charcoal. Animal charcoal is obtained by the destructive distillation of bones and is used as a common decolorizing agent. Sugar charcoal is obtained by the action of concentrated sulfuric acid on sugar. It is the purest man-made form of carbon. Coconut charcoal is obtained by the partial combustion of shells of coconuts. Wooden charcoal is obtained by the partial combustion of wooden material. Gas carbon is obtained during the refining process of crude oil, while lamp black is obtained by the partial combustion of vegetable oils. These are all examples for amorphous forms of carbon. For crystalline forms, three forms are considered. Diamond and graphite are natural forms, while fullerenes are man-made crystalline allotropic forms of carbon. We have to see the detailed structures of crystalline allotropic forms, that is structure of diamond, graphite and fullerenes. Structure of diamond. In case of diamond, each carbon atom undergoes sp3 type of hybridization in the first excited state. Carbon atomic number is 6, electronic configuration is 1s2, 2s2, 2p2. Arrangement of electrons in the valency shell can be represented like this. With this type of configuration, what we call ground state electronic configuration, only 2 bonds are possible, but carbon shows tetravalency in most of its forms. So, in the excited state, one of the 2s electron will be promoted to 2p level, and the configuration in excited state can be represented as 1s2, 2s1, 2p3. The arrangement of electrons will be like this. After the process of excitation, hybridization takes place. The 2s orbital and all the 3 2p orbitals combine together to form 4 sp3 hybrid orbitals. All the hybrid orbitals have one unpaired electron, and all the 4 hybrid orbitals are involved in the formation of bonds with other carbon atoms. In diamond, each carbon atom is tetrahedrally linked with 4 other carbon atoms. The structure is as shown in the diagram. In diamond, each carbon atom is tetrahedrally linked with 4 other carbon atoms. As you can see in this diagram, the black colored balls represent carbon atoms. Each carbon is tetrahedrally linked with 4 other carbon atoms. The structure extends up to infinity. Hence, the final structure of diamond becomes a giant polymeric tetrahedron. This represents the 3-dimensional arrangement of carbon atoms in diamond. The carbon-carbon bond length in diamond is 1.54 angstrom units, and carbon-carbon bond angle is 109 degrees 28 minutes. This structure is highly compact in nature, and all the 4 valence electrons of carbon are involved in bond formation. Even though number of atoms are present, they are all present in a very small space. Hence, the density of diamond is very high. Based on the structure of diamond, we should explain some of the physical properties like melting point. Diamond has a very high melting point of 4200 degrees centigrade, which is somewhat abnormal for a covalent crystal. No doubt, individual carbon-carbon bond strength is less, but in case of diamond, large number of such carbon-carbon single bonds are present, and to break all those bonds, it requires a lot of energy. Hence, the reason for high melting point of diamond is its giant polymeric tetrahedral structure and presence of large number of carbon-carbon single bonds. Then, diamond has a very high refractive index value. Diamonds have very high refractive index value. It is also because of their structure only. When a ray of light enters into the crystal structure of diamond, it will undergo multiple reflections. As a result, when light falls on a diamond, it starts glittering. The phenomenon involved is a total internal multiple reflections of light, and as a result, the refractive index value of diamond is very high. Coming to conductivity, diamond is a non-conductor of electricity. Again, this property is also because of its structure. For a substance to act as a conductor, either it should have free electrons or free ions. But in case of diamond, all the 4 valency electrons are utilized in the formation of strong carbon-carbon single bonds. Due to absence of free electrons, the diamond is a non-conductor of electricity. How to assess the quality of a diamond? The quality of a diamond is assessed on a principle called as 𝗧𝗦 principle. The 4 C's that stand are: first C is for carat, second C is for color, third C is for clarity, and fourth C stands for cut. Carat indicates the weight of diamond. 1 carat is equal to 200 milligrams. With increase in the number of carats, weight of the diamond also increases. Color: 100% pure diamonds are supposed to be colorless in nature. However, due to the presence of impurities, particularly metallic oxides, diamonds carry beautiful colors. However, lighter the color, more pure is the diamond or more quality is the diamond. Similarly, the diamond has to be clear. That clarity can be assessed by means of crystallographic studies. The fourth parameter, cut, it is purely human effort and skill. Based on these 4C values, the diamond quality is assessed, and that principle is known as the 4C principle. Structure of graphite. In graphite, each carbon atom undergoes sp2 type of hybridization in the first excited state. The ground state electronic configuration of carbon is 1s2, 2s2, 2p2. Arrangement of valency electrons can be indicated like this, and configuration in the excited state is 1s2, 2s1, 2p3. After the process of excitation, sp2 hybridization takes place due to the combination of one 2s orbital and two 2p orbitals. Each carbon is left out with one pure p orbital along with one unpaired electron. It does not participate in bond formation. This electron, which is not participating in the bond formation, is called as a free electron. Hence, each carbon atom in graphite is associated with one free electron. The final structure of graphite can be represented as shown in the diagram. Structure of graphite. In graphite, each carbon atom is linked with three other carbon atoms in a trigonal planar fashion by making use of sp2 hybrid orbitals. Overall structure is a layered structure. In each layer, hexagonal rings of carbon atoms are present in a large number. As you can see in the diagram, the black colored balls represent carbon atoms. Each carbon is linked with three other carbon atoms in a trigonal planar fashion. This represents one layer of graphite that consists of hexagonal rings. Between the hexagonal rings, carbon-carbon single bonds are present, and these layers are bound by means of van der Waals forces of attraction. The carbon-carbon bond length in the layers is 1.42 angstrom units, and the distance between any two layers is 3.35 angstrom units. The overall structure of graphite is called giant polymeric hexagonal layered structure. The bond angle is 120 degrees. Fullerenes. Fullerenes are also crystalline allotropic forms of carbon. These are purely man-made allotropic forms. These are obtained by the strong heating of graphite to high temperature and high pressure in the absence of air. Aggregate of carbon atoms will be obtained, and the common fullerene is known as Buckminster fullerene, that is represented with the formula C60. In any fullerene, the carbon atom undergoes sp2 type of hybridization. The structure of Buckminster fullerene is as shown in the diagram. In Buckminster fullerene, we can see 5-membered carbon rings and 6-membered carbon rings. 6-membered carbon rings are known as hexagonal rings, whereas 5-membered carbon rings are called as pentagonal rings. In total, there are 20 hexagonal rings and 12 pentagonal rings in the structure of Buckminster-Fullerene. As this structure resembles the structure of a football, it is also known as a football structure, which is applicable for Buckminster-Fullerene, and its molecular formula is C60. Compounds of carbon. In this topic, we will concentrate on oxides of carbon. Carbon gives 3 types of oxides. The familiar ones are carbon monoxide, carbon dioxide, and carbon suboxide. Carbon monoxide and carbon dioxide are familiar. Carbon suboxide is an unstable oxide of carbon. Its structure is linear and is represented like this, with each carbon atom undergoing sp type of hybridization. However, suboxide is unstable in nature, so we will concentrate only on carbon monoxide and carbon dioxide. We have to see the preparation methods, properties, and uses of these 2 oxides, carbon monoxide and carbon dioxide. Carbon monoxide. Preparation methods. These preparation methods can be studied under 2 headings: laboratory methods and industrial methods. In the laboratory, carbon monoxide can be prepared by the partial combustion of carbon. Pure carbon monoxide can be obtained by the dehydration of formic acid using concentrated sulfuric acid. When formic acid is heated in the presence of concentrated sulfuric acid, like this, elimination of water molecule takes place, leading to the formation of carbon monoxide and water. On a large scale, carbon monoxide is prepared by Bosch process, also called as coal gasification method. This method comes in the preparation of hydrogen also. In this, steam is passed over red hot coal or coke. Coke, being a strong reducing agent, takes away oxygen from steam. We get a mixture of carbon monoxide and hydrogen. In place of coal, we can make use of gaseous hydrocarbons also, like methane. When methane is made to react with the steam in the presence of catalyst, we get a mixture of carbon monoxide and hydrogen. This mixture has to be subjected to a process called as quenching, that involves sudden cooling. On sudden cooling, carbon monoxide gets liquefied, and in that way the mixture can be separated. The mixture of carbon monoxide and hydrogen is also called as water gas, syngas, as well as blue gas. Properties of carbon monoxide. Carbon monoxide is unstable in nature, readily undergoes oxidation to give carbon dioxide. Because of this nature, carbon monoxide is used as a powerful reducing agent in the metallurgy of iron and zinc, because carbon monoxide can readily reduce oxides of iron and zinc to corresponding metals. For example, when iron oxide is heated with carbon monoxide, we get iron and carbon dioxide. Similarly, zinc oxide gives zinc and carbon dioxide. Equations are to be balanced. So, these are the balanced equations. In these reactions, carbon monoxide is acting as a reducing agent and it is reducing metallic oxides to corresponding metals. Carbon monoxide is an unsaturated compound. It can develop dative bonds with most of the transition metal ions. It can develop complex compounds with hemoglobin present in the blood. Hence, carbon monoxide acts as a highly toxic gas and it converts hemoglobin to carboxyhemoglobin that loses the capacity to transport oxygen. Uses of carbon monoxide. Even though highly toxic in nature, carbon monoxide is used in the metallurgy of iron and zinc. Earlier days, mixtures of carbon monoxide were used as industrial fuels, whose names are relevant for the entrance examinations. Carbon monoxide and hydrogen mixture is known as water gas. A mixture of carbon monoxide and nitrogen is called as a producer gas. Mixture of carbon monoxide, hydrogen and nitrogen is called as a semi-water gas. Mixture of carbon monoxide, hydrogen, nitrogen along with gaseous hydrocarbons like methane, ethane, etc. were called as carbureted water gas. All these were used as industrial fuels in the earlier days. However, their usage has been limited now due to highly toxic nature of carbon monoxide. Particularly, water gas is still being used not as an industrial fuel but as a powerful reducing agent in the metallurgical operations. Carbon dioxide, CO2. Carbon dioxide can be prepared by the oxidation of carbon monoxide. Alternatively, by burning carbon in excess of oxygen, carbon dioxide can be obtained. Most of the carbonates undergo the process of decomposition to give carbon dioxide. For example, if calcium carbonate is heated, it will decompose to give calcium oxide and carbon dioxide. Or by the action of dilute mineral acids on carbonate salts, we can prepare carbon dioxide in a convenient manner. For example, when sodium carbonate is made to react with dilute hydrochloric acid, we get sodium chloride, water and carbon dioxide as the products. These are the various methods used for the preparation of carbon dioxide in the laboratory. In nature, carbon dioxide is formed by the combustion of fossil fuels and by the process of respiration of animals. Properties of carbon dioxide. Carbon dioxide, being a non-metallic oxide, is slightly acidic in nature. It readily dissolves in water at low temperature and high pressure to give carbonic acid, a weak dibasic acid. The mixture of carbon dioxide and water is called as aerated water, or in common language, soda. It reacts with metallic oxides like calcium oxide to give corresponding salt-like substance, calcium carbonate. When passed through an aqueous solution of sodium hydroxide, it gives sodium carbonate. When carbon dioxide gas is subjected to high pressure at a temperature of 31.1 degree centigrade, gaseous carbon dioxide is converted into solid carbon dioxide. The solid carbon dioxide formed is called as dry ice. Dry ice is associated with the property of sublimation. So, when it is heated, again it is directly converted back into gaseous carbon dioxide. The reactions indicate a slight acidic nature of carbon dioxide, while the fourth property, that is conversion of gaseous carbon to solid carbon dioxide form, indicates a physical change. In carbon dioxide, carbon atom undergoes sp hybridization. Structure is linear. It can be represented like this. The structure is linear with a bond angle of 180 degrees. Uses of carbon dioxide. In nature, carbon dioxide is responsible for photosynthesis that takes place in plants and is involved in the formation of carbohydrates. In day-to-day life, solid carbon dioxide, which is known as dry ice, is used for the transportation of dairy products and meat compounds of silicon. Here we will come across oxides of silicon and silicones. Silicon gives silicon dioxide, which is also known as silica, whereas silicones are organic polymers involving silicon. Silica is available in nature in two forms. One is a crystalline form, another one is a amorphous form. Crystalline form of silica is called as quartz, whereas amorphous form is known as sand. It is available in nature in plenty. Silicon dioxide can be prepared in the laboratory by the following methods. One method is by the strong heating of silicon in oxygen. Alternatively, silicon tetrachloride is hydrolyzed. Structurally, silicon tetrachloride can be represented like this. When water is added like this, the bonds will break down. OH part of water is added to silicon, H part is added to chlorine. In that way, we get SiOH taken 4 times, or it can also be represented as H4SiO4, silicic acid. This silicic acid on strong heating loses water molecules to give silicon dioxide, which is 100% pure. These are the preparation methods of silica or silicon dioxide. Properties of silicon dioxide. Just like carbon dioxide, silicon dioxide is also an example for non-metallic oxide. Hence, it is slightly acidic in nature. However, compared to carbon dioxide, it is less acidic. When fused with sodium hydroxide, silica gives a compound known as sodium silicate. This sodium silicate is commonly called as water glass. A similar reaction takes place with sodium carbonate also. In place of water, now carbon dioxide is obtained as a side product. In silicon dioxide, silicon atom undergoes sp3 type of hybridization. The structure is a giant polymeric tetrahedral. Because of the alternating arrangement of silicon and oxygen atoms, this structure is also known as a mat-like structure. Silicon is in sp3 hybridized state, and the final structure is called as giant polymeric tetrahedron. Because of the polymeric structure, silicon dioxide exists in the form of a solid state and is insoluble in water, whereas its analogous compound carbon dioxide, as it exists in monomeric form, is soluble in water and exists in the form of a gas. Uses of silica. The crystalline form known as quartz is used in the making of optical lenses, prisms, and in the manufacturing of watches. Amorphous form of silica is used as a construction material. It is also used for the preparation of pure silicon as well as silicon carbide. Pure silicon is used in the making of memory devices, while silicon carbide is used as abrasive. It is the hardest man-made substance. Pure silicon required for the manufacturing of memory devices is prepared by the reduction of silica with electropositive metals like magnesium, whereas silicon carbide is prepared by heating silica with coke in an electrical furnace. Organosilicon polymers are called as silicones. These are prepared by heating silicon with alkyl halide. Any alkyl halide can be used. For example, if silicon is heated with methyl chloride, first we get dimethyl dichlorosilane. This, when subjected to hydrolysis, these bonds will break down like this, and with the elimination of HCl molecules, we get this compound, which is known as dimethyl dihydroxysilane. This dimethyl dihydroxysilane, or generally speaking dialkyl dihydroxysilane, is the monomer of this polymer silicone. These molecules will be attached with each other by means of a polymerization mechanism known as condensation polymerization, and in that process long chains of silicones are obtained. For example, two monomers are attached with each other by means of condensation polymerization like this. On heating, one water molecule is eliminated and we get two monomers of dialkyl dihydroxysilanes undergo condensation polymerization to give this as a dimer. The process of addition can take place on either side, leading to the formation of a polymer, and those polymers are called as silicones. The reaction comes to an end when the terminal OH groups combine together, and in that process one water molecule is eliminated. Then the resultant polymers obtained are called as cyclic silicones. Silicones are chemically inert, non-conducting and water repelling polymers. Hence, these are extensively used in the making of hand gloves that are used for surgical operations as well as by the electricians. Silicones are also extensively used in the making of raincoats and tarpaulin sheets, etc. Silicones are nowadays being used in the form of greases also for special equipment. In this topic, fourth year group elements, we have discussed the general physical properties followed by general chemical properties as well as allotropic forms of carbon. Under the heading of allotropic forms of carbon, we have to study in detail about the structural features and properties of crystalline allotropic forms, that is diamond, graphite and fullerene. Then in specific compounds, we have studied in detail about oxides of carbon and silicon. Now let us see some of the previous questions that came in various entrance examinations based on 4th A group elements. When a small amount of arsenic is doped into silicon, the given options are A. Conductivity decreases, B. It becomes p-type semiconductor, C. It becomes n-type semiconductor, D. There is no change in its conductivity. Correct option is C. It becomes n-type semiconductor. Second question, which of the following is incorrect? Given options are diamond is a better thermal conductor than graphite, diamond has a higher refractive index than graphite, graphite has a higher bond order than diamond, conversion of graphite to diamond requires high pressure and low temperature. Correct option is D. Conversion of graphite to diamond requires high pressure and high temperature, but in the given options it is specified as low temperature. Hence, that is the incorrect answer. Which of the following is not affected by alkalis? Given options are silicon, germanium, diamond and tin. Correct answer is C. Diamond. Diamond is not affected by either acids or bases at low temperatures. Fourth question, graphite is used in the making of crucibles because A. It has layer lattice structure, its density is less, bonds are strong with the bond order nearly 1/3, it is chemically more reactive than diamond. Correct answer is C. Bonds are strong with a bond order nearly 1/3. Fifth question, the covalent radius of germanium is close to that of silicon because silicon is more dense, 3D10 in germanium gives poor shielding, 2s2 gives better shielding in silicon, metallic nature increases. Correct option is B. 3D10 in germanium gives poor shielding and hence its radius is closer to that of silicon. Sixth question, the element of group 14 with the least melting point is, given options are silicon, tin, germanium and lead. Correct option is tin. Seventh question, which of the following pairs form cations? Given options are carbon silicon, silicon germanium, carbon germanium, tin and lead. Correct option is D. Tin and lead. Eighth question, which pairs of elements have closure atomic size? Given options are carbon silicon, germanium tin, tin lead, silicon and tin. Correct option is C. Tin and lead have similar atomic radii. Ninth question, even though carbon, silicon are nonmetals, they have higher melting points than others because, given options are they exist as covalent solids in 3D networks, the bonds in their molecules are strong, carbon-carbon double bond and carbon-carbon. Even though carbon, silicon are nonmetals, they have higher melting points than others because. Correct option is A. They exist as covalent solids in 3D networks. In giant polymeric structures, the melting points and boiling points will be comparatively higher than others. 10th question, which of the elements of group 14, germanium, silicon, carbon and lead exhibit different electronegativity from others? Given options are silicon, germanium, carbon and lead. Correct option is carbon. Carbon electronegativity is 2.5, which is different from rest of the elements which have a uniform value of 1.8. 11th question. The increased metallic character is evident in A. Lower melting point, B. Lower boiling point, formation of cations, formation of acidic solutions by their oxides. Correct option is C. Formation of cations. 12th question. Germanium is given options are more metallic than silicon, less metallic than silicon, forms more acidic and less basic oxide, forms more basic and less acidic oxide. Correct option is D. Forms more basic and less acidic oxide. 13th question. Which is incorrect as we move down in group 14? Correct options are malleability increases, conductivity increases, luster increases, ductility decreases. Correct option is 4. Ductility decreases. 14th question. Which compounds of tin and lead are likely to be more ionic? A. Fluorides, B. Iodides, C. Bromides, D. Sulfides. Correct option is A. Fluorides. 15th question. Carbon, silicon differ from other elements in group 14 in the following aspects except A. Outer electronic configuration, B. Absence of d orbitals in n-1 shell, C. Presence of sp.d electrons, D. Electronegativity value. Correct option is A. Outer electronic configuration. 16th question. Carbon differs from other elements in group 14 regarding A. Absence of d orbitals in the outermost shell, higher electronegativity value, more catenation, D. All the above. Correct option is D. All the above. 17th question. Concentrated nitric acid has no action on A. Tin, lead, graphite and diamond. Correct option is D. Diamond. Diamond doesn't react with any acid or base under normal conditions. 18th question. On heating with fluorine, a difluoride is given by. Given options are silicon, lead, tin and germanium. Correct option is B. Lead, because of inert pair effect. 19th question. Which of the following changes take place readily? Given options are Sn plus 4 to Sn plus 2, Pb plus 4 to Pb plus 2, GeO2 to GeO, SiO2 to SiO. Correct option is B. Lead dioxide is readily converted into Pb plus 2 because of inert pair effect. 20th question. Which of the following is more ionic? A. SnCl2, B. SnCl, C. PbF2, D. PbO. Correct option is C. PbF2. 21st question. Which is not a reducing agent among the following? Given options are carbon monoxide, germanium chloride, lead chloride and stannous chloride. Correct option is C. Lead chloride. 22nd question. Which of the compounds of M plus 4 state is more covalent? In place of M, the elements considered are lead, tin, germanium and silicon. Given options are Pb plus 4, Sn plus 4, Ge plus 4 and Si plus 4. Correct option is D. Si plus 4. 23rd question. Plus 2 state is more stable than plus 4 state in lead because given options are to lose 2 electrons is easy, of more hydration energy of plus Pb plus 2, of poor shielding effect of 4F14 and 5D10, of better shielding effect of NS2. Correct option is C. of pore shielding effect of 4F14 and 5D10. 24th question. Methane is formed by the action of water on. Correct option is C. Beryllium carbide. 25th question. In carbonate ion, the carbon-oxygen bond order is. Given options are 2, 3, 1, 1, 1/3. Correct answer is D. 1, 1/3. 26th question. Correct statement about carbon monoxide is. Given options are it is a reducing agent, it is a strong ligand, it undergoes addition reactions and dissolves in ammoniacal cuprous chloride. All the above statements are correct. Correct option is D. All the above statements are correct. 27th question. The hybridization of carbon in carbon monoxide molecule is. Given options are sp3, sp in the ground state, sp in the excited state, sp2. Correct option is B. sp in ground state. 28th question. The oxidation states of lead in red lead Pb3O4 are. Given options are +2 only, +4 only, +4 and +2, D +8/3. Correct option is C. +4 and +2. 29th question. Which of the following is not an amphoteric oxide? Given options are SNO, PbO, SNO2 and CO. Correct answer is D. Carbon monoxide. It is a neutral oxide. 30th question. Which one of the following reacts readily with the silica at room temperature? Given options are HCl, NaOH, HF and dilute sulfuric acid. Correct option is C. HF. The coordination numbers of metal and oxygen in their dioxides in group 14 are. Given options are 4:4, 6:4, 6:3, 3:6. Correct answer is C. 6:3. 32nd question. Which of the following is not a silicate? Given options are mica, feldspar, zeolite and fluorspar. Correct answer is D. Fluorspar. It is not a silicate mineral. 33rd. Which metal silicates are water soluble? Given options are aluminum, calcium, magnesium, calcium, aluminum, sodium, sodium and potassium. Correct answer is D. Sodium and potassium. They are water soluble in nature. 34th question. Which is wrong regarding silicates? Given options are silicon oxygen bond is 50% ionic and 50% covalent. The radius ratio of silicon +4 and O-2 is 0.29 with a coordination number of 4 for silicon. Polymers of silicate tetrahedral are formed by sharing corners. The metal atoms form CCP lattice and silicon oxygen atoms occupy the voids. The correct answer is D. The metal atoms form CCP lattice and silicon oxygen atoms occupy the voids. 35th question. General formula of cyclic silicates is. These are the given options. Correct option is first one, SiO3 taken n times to the power -2n. 36th question. Cement is made by heating at 1450 to 1600 degrees centigrade a mixture of A. Limestone and clay, limestone and sand, limestone, sand and clay, sand and clay. Correct answer is C. Limestone, sand and clay mixture is heated to get cement. 37th question. The main constituents of Portland cement are. Given options are calcium oxide, aluminum oxide, silicon dioxide, aluminum oxide, calcium silicate, calcium aluminate, calcium oxide, silica, alumina and iron oxide. Correct option is C. 38. A small amount of gypsum is added to cement. The purpose is, given options are to increase the strength, to make cement white, to delay the setting, to resist action of acids. Correct option is C, to delay the setting time. 39th question. Which of the following regarding the setting of cement is not correct? Hydration of calcium aluminates and calcium silicates, evolution of heat, hydrolysis of M+3 and M+2 ions, D. Formation of SiO2. Correct option is D. Formation of SiO2. 40. Which is correct among the following? A. Excess lime in cement causes cracks and loss of it makes cement weak. Excess silica causes slow setting and excess alumina causes quick setting. Without iron, the cement is white. D. All the above. Correct option is D. All the above.